Thanks everyone for coming to the talk, and thanks Andrew for organizing this nice workshop for hotel revenue management. So I'm Zifeng, and I'm an assistant professor from University of Notre Dame. So today I want to talk about this project called Modeling Consumer Choice and Optimizing Assortment under the Threshold Multinomial Logic Model. So this is a joint work with Professor Wang from Johns Hopkins and also with Chenxu from Nanjing University. Okay, so I'll quickly talk about the problem setting, and then I'll introduce the model we propose, which is the threshold multinomial logic model. And then I will talk about the assortment optimization side, and if time permits, I will talk about the numerical results and some applications. Okay, so we start with the classical MAL model, which has been introduced in this workshop before, right? So basically, the traditional MAL model assumes that given an offer set S, each of the item assumes a random utility in each of the item I in this offer set assumes a random utility, right? So it can be this capital UI can be decomposed into a nominal utility UI and into an uncertainty part CI, right? So the consumer has prior knowledge, has expectation, which is this UI. So the consumer knows this little UI, but due to idiosyncratic errors, they don't really know this capital UI, right? So they need to actually solve this CI, right? So ML model assumes that then the consumer will examine all the items in this S and then solve all the uncertainty CI, and then we'll go ahead and find the one, choose the one with the highest realized utility capital UI, right? And then if we follow this format, and the choice probability will be written at this form, right? So basically, it's own utility divided by the sum of all the utilities. Right? However, sometimes in reality, the consumers may not make decisions that way, right? So a lot of empirical and behavioral evidence actually suggests that the consumer sometimes make decisions using a two-stage choice process. The two-stage is as follows. So basically, given an offer set S, the consumer will first quickly apply a screening rule to form a consideration set. And this consideration set CS is a subset of all the offer set of the offer set. And then in the second stage, only in the second stage that the consumer will closely examine all the items and solve the uncertainties. But that only happens for all the items in this consideration set. Okay. So the reason is because, as suggested by this empirical and behavioral work, the reason why is consumer using this two-stage choice process is that sometimes there are just a lot of items to choose from, right? And it costs time and effort to fully examine all the products. So that's why sometimes they follow this two-stage choice process. And one of the promising models to model this two-stage choice process is this so-called threshold loose model, or the T-loose model, proposed by these two papers in economics. So basically, they assume the consumer in the first stage, how this screening rule works. They assume the consumer using a dominance rule to form the consideration set. So basically, the consumer has a threshold delta, and this delta is not negative. So given all the items S, so for all the items I in this offer set S, in order for this I to be passed to the consideration set, it needs to fulfill this condition here. So this is called the dominance rule. So basically, the nominal utility, the prior knowledge of the consumer for the utility of this item I needs to pass a threshold, and the threshold is basically defined as this. So basically, it needs to pass the maximum nominal utility in this offer set minus a threshold, right? So you can think this delta is the tolerance of the consumer. If this delta is infinity, basically the consumer doesn't do any screen. But if this delta is very small, then the consumer will screen a lot of items out, right? And then so after we form this consideration set, then the consumer will choose the one with the highest realized utility only within this consideration set, right? So this is a T-loose model, right? So here's an example, right? So suppose we have wine, beer, and soda, right? So the nominal utility of wine UW is 3, for beer is 2, and for soda is 1, right? And then the threshold parameter is 1.5. And if we offer the consumer all the 3 items, actually the consumer will only consider wine and beer because UW minus US is 2, which is higher than 1.5, right? So they will automatically, in the first stage, they will screen out soda. They will never consider soda. But if we only offer wine and beer, and the consideration set can also just be the same as offer set, nothing got screened out. Okay, so this threshold threshold loose model will imply the following choice probability. So basically, given all the nominal utilities and given the threshold delta, all the can be classified into 2 classes, right? So if you are not included in the consideration set, you will never be chosen, right? So it's 0. But if you are included in the consideration set, this is just a MNL model, right? So basically, I compare my own utility with the sum of all the utilities of all items in this consideration set, right? So this is the T-loose model. Now, the advantage of T-loose model obviously is it's simple and interpretable, right? So it uses a dominance rule. It uses a very simple dominance rule to describe the mechanism how consumer form the consideration set, right? And the authors of T-loose model show that it can offer more flexible substitution patterns and can elevate the IA properties. And assuming the true knowledge of this delta and nominal utility yield, the following papers actually studies the pricing optimization for this T-loose model. Okay, however, there are also obvious limitations of this T-loose model. So obvious limitation is that it has a quite restrictive assumption that assumes that all the consumers follow the same threshold delta, right? This may not be reasonable in practice because some consumers may be willing to spend more time to search for the characteristics of each item. Some maybe they are busy and then they don't want to spend any time, right? So some consumer may have a higher delta and some might have a smaller delta, right? So this however, if we T-loose model doesn't allow consumer heterogeneity, right? And also it might imply 0 choice probability for certain item because of this mechanism here, right? And this may create some problems, and specifically the T-loose model will be very difficult to be estimated from real data, right? So theoretically this is a nice model, but it cannot be empirically verified. And the reason is that this choice probability, now this choice probability here, if you figure it's quite simple, but like just by simple algebra, you'll figure out this choice probability is going to be a discrete function of this delta and this nominal utility yield, right? So intuitively, you can think about it's because I have a gap here. I jump if an item fall out from the consideration set, it immediately becomes 0. So there will be an abrupt change for this choice probability, right? And if I want to estimate this parameter delta and yield, it's going to create a lot of numerical error, issues, right? Because my likelihood is not even continuous, right? And also this delta is not point identifiable, right? So which meaning that, so given the same yield here, I can find 2 delta that give me exactly the same choice probability for all the items in this S, right? So this model is not uniquely identified, right? So that's this limitations motivates us to propose the random threshold multinomial logic model, or we call it TMNL model. Okay, so basically the idea is very simple. So we follow the general framework of the T-loose model. We still assume the consumer use the dominance rule to do the consideration set formation. The difference is that instead of assuming this delta to be a fixed number, now we assume this delta to be a continuous random variable. And this continuous random variable it's on the positive axis and it follows some probability family. Like, for example, this delta can be like a log normal distribution, can be a gamma distribution, and so on and so forth. And we call this probability distribution f delta tau, and tau is the parameter to be estimated, right? So this TMNL model now allows consumers to have different delta, right? So because each consumer basically their delta is sampled from this commonly from this common from this common distribution, right? So in this way, this is similar to the mixed logit model, right? So mixed logit model assume I have an MNL model, but the specific case, the beta of each of the consumer is sampled from a common distribution. So first we have a very simple lemma 1. So basically assuming this lemma 1 tells us that our proposed TMNL model can incorporate both the T-loose model and the standard MNL model as a limiting case. The intuition is very simple. So you can think this delta, this is a random delta now, right? So, but if I use mu delta to represent the expectation of delta and sigma delta to represent the variance, the standard deviation of delta. The T-loose model basically assumes this delta is fixed. So in order to achieve that, basically I can lower the volatility or the standard deviation of this TMNL delta to be 0. And to approximate MNL model, so basically it means the consumer doesn't do thresholding. So basically I can increase this mu delta to infinity, and at the same time I lower the uncertainty, and then I will recover the MNL model. And more importantly, I have this following lemma. So basically under the TMNL model, the choice probability of item I in an offer set will be able to we can write it as the integral form here. Okay, so basically because this delta here is random, right? So basically I take a further expectation of this delta, and you'll find that it's very simple. It takes this form here, this QI here. So this form is the choice probability of the T-loose model given a specific delta. Now I just basically integral all of them together, and I will arrive at the TMNL model. And actually this integral looks complicated, but actually it can be further simplified into a very simple summation form using order statistics. But due to time limit, I'll skip that part. Anyway, because of this, because of the because we introduce this this randomness of inside this delta, and we write this this whole thing in an integral form, you'll find that although this Q is a discontinuous function of U and delta, but the discontinuity only happens in a very infinitesimal. Okay, so that basically, although there is this discontinuous in this integral, but after I integrate everything out, this choice probability is actually continuous, and it is not just continuous; it also almost everywhere differentiable with respect to this U, and differentiable with respect to tau. Okay. So we have some other properties of TMNL model, but due to time limit, I'll skip it. Okay. So here is the example. So so suppose I have an offer set. It has a 0, 1, 2. Right, and the nominal utility is U0, U1, U2. So I fix U0 and U1 to be 0 and 1. So I only vary U1. Okay, and I also assume this threshold parameter delta, it follows a log normal distribution with mean 1 and variance 0.5, standard deviation 0.5. So now I plot the choice probability for the item 0 and for item 1. Now you can see that the choice probability is continuous, right? So on both of the plot, it's continuous, but it almost everywhere differentiable. The only non-differentiable point is here and here. Okay, when this U1 is 0 or 1, or when there's ties. So when there's ties among U, there will be non-differentiable. That's where the non-differentiability appears. Okay, however, even if at this point it is non-differentiable, it is semi-differentiable, meaning that both the left and the right derivative exist. Okay. So now, since the choice probability of the TMNL model is nicer, right? It's much nicer. It's almost everywhere differentiable, so that we can actually use MLE to estimate this thresholding effect and to empirically verify whether there is actually a thresholding effect in practice or not. Right. So the MLE basically follows the MLE basically follows the standard procedure, right? So we assume the data set consists of capital G consumers, and each of the consumer have an offer set SG, right? And they randomly then they chose an item called CG, right? And we assume that the nominal utility of this item I in this offer set SG is a linear combination of the characteristics of those product attributes. So then we will have a beta parameter to be estimated. And then we also assume each of the consumer will have this random threshold delta G. This delta G follows is sampled from this threshold distribution f delta tau. Right? So we have two parameters, beta is the taste of the consumer, and then we have the tau. Tau is the thresholding effect of the consumer. And then we just formulate the log likelihood function, and we can further write this out as the integral form and then as the summation form. So everything it can be done, can be optimized numerically. So we define the MLE as the maximizer of this log likelihood function. Okay, so this log likelihood function, we show that in general this function is actually not globally concave. Okay, but it does have a closed form gradient and Hessian function. So we can basically plug this log likelihood function into a generic solver, right? And then we provide the gradient and the Hessian. You can do gradient descent or some other algorithms, right? So we can solve for the maximizer of this log likelihood function. And we in our paper we further provide rigorous statistical guarantees for this MLE because this is a new model, right? So this is not the standard MNL model. So that's why we provide a rigorous statistical guarantee for this MLE. So basically, under some mild conditions, which I didn't include here due to time, in the interest of time, so we can have consistency. So basically, meaning that if our sample size grow larger and larger, our estimator will converge to the true parameters. And then we will also have a symptotic normality. And so basically, this theta hat will converge to a normal distribution, and this sigma is the Fisher information matrix. And we can consistently estimate this Fisher information matrix, and then we can construct confidence intervals for this theta hat, right? And as I said, although this function here is not globally concave, but we can show that asymptotically it is locally concave within the MLE theta hat. Okay, so basically we can find so with this sample size grow larger and larger, we can find within the whole parameter space theta there is a unique maximizer of this likelihood function, and further around this maximizer there is a fixed neighborhood such that this log likelihood function is concave, but only in this fixed neighborhood. Okay, so here is some numerical, so here are some visualizations. Right, so we can see that, so I plot the log likelihood function with respect to beta 1 and beta 2. You can see that this function in general looks quite nice, but obviously this function is not concave. Sorry, I plot the negative log likelihood function, so it's not obviously not convex. Right, so you can see here it's not convex, but within around the true change point, around the true parameters, you can see that it looks locally concave. Right? So we also studied the assortment optimization under both the T-loose model, since it's not done in the literature yet, and for the TML model as well. So the generic assortment optimization problem basically given is as follows, right? So I given a set of all the products. I want to find a subset S within this N such that it maximizes my expected revenue, right? So RI is marked up, and then this probability this probability is the probability of chosen I given the offer set S. Right? So for T-loose model, this P is the choice probability implied by the T-loose model. For TML model, is the one implied by TML model. So we first look at the assortment optimization for T-loose model. So unlike the MNL, we show that the Markov order assortment is not optimal anymore, but we can provide a tight performance bound, which is 1 over 2. Okay, so and although the Markov order assortment is not optimal, but there's a quasi Markov order assortment that is actually optimal, and it can be solved in n-squared operations. Okay, so and the basic idea is I need to use the dominance rule. So once I figured which item is the dominant item, then I can figure everything out quite nicely. Okay, but due to time limit, I will skip it. Okay, and then things change for TML model. We first show that under the newly proposed TML model, assortment optimization is NP-hard, so it cannot be solved efficiently. And an important intermediate step to show this result is that we have this following lemma, is that once we fix the total number of available items n, and we fix all the nominal utilities u, we can view this TML model can be viewed as a mixture of T-loose model. So basically, I can be viewed as a mixture of n-squared number of T-loose models. Okay, and this mixture of T-loose model turns out is NP-hard to solve. Okay, so although it's NP-hard to solve, and then later we derive a dynamic program that can help us to return optimal assortment in pseudo polynomial time, or we can design we can further discretize this DP, and then we'll get FPTAs for this original problem. The intuition again is focused on the dominance alternative. Once we figure out which item dominant, and then we can figure out the rest. And while the important observation to formulate a dynamic program is to realize that if I have a mixture of T-loose model, basically they will have a very nice property that their consideration set will be nested based on the delta, based on which one has the largest delta and which one has the smallest delta. And all the T-loose model will have a nested consideration set. And that helps us design a very efficient dynamic program. Okay, so for the time's sake, I'll quickly go through this. We first did a simulation study. So basically, we simulate the data from a true TML model, and we use the MLE to estimate the parameter. Okay, so we increase the sample size from 2,000 to 5,000 to 10,000, and you can see that and we repeat the experiment 500 times, and we take the average. And you can see that the estimated parameters from the MLE is getting better and better. So the true parameter is 0.5, 0.75, 0.25, 0.5, and 0.1. You can see that with G goes up, it matches our theory, right? So the estimation becomes better, and the standard deviation also drops. We also construct the confidence interval, and you can see that the coverage rate is around 95%. Yeah, we tested the data. We tested our TML model on phishing data and also on GD.com data from this some paper. Okay, so we find that we compare with ML, or we compare TML model with log normal threshold, with gamma threshold, with the ML model and the mixed logit model. We find that in general, it does improve the performance. Right? So for the phishing data, improve the, for example, revenue prediction by around 3%, and improve some other market share prediction by more. Okay, and for the GD.com data, it also improved the revenue prediction accuracy and stuff like that. Okay, but in general, for the GD.com data, the improvement is lower than from the phishing data. Now, the phenomenon is explained by these two graphs here. So based on the estimated TML model for the phishing data and GD.com data, we can plot out the consumer's decision grid. So basically, the histogram here is the nominal utility minus the nominal utility of dominance item minus all the other items, and the red curve is estimated log normal distribution. You can see that for the phishing data, the thresholding effect is more dominant, not more prominent. For the GD.com data, the threshold effect is less prominent. Okay, that's why for the phishing data we achieve more improvement. Okay, so and obviously this TML model can be further used as it can be find potential applications in hotel revenue management, right? Because consumer may use this two-station a two-stage decision process in this in choosing a hotel room or choosing what type of upgrade they want to choose. Okay, so this is just a brief summary, and for the future extension, we can further study the pricing optimization, or we can combine the TML model further with the mixed logic model. So thank you, and this is my presentation. So if you have any question, I'm happy to answer any.
Can you hear me?
Yeah.
Okay. Yeah, I just have one question that in your model, the screening seems like a one-dimensional, like search for delta with a product characteristic. What if, have you considered the case where the screening is high-dimensional, like you screen on several dimensions on different characteristics of a product? How does that affect the model?
Okay. That's a very good question. I don't think I have thought about it, but like I think the reason why we screen across one dimension is that we have this assumption, right? So we assume the nominal utility is a linear. So we don't screen on this x, right? We screen on the nominal utility. So that's why this whole thing becomes one dimension, right? But I guess if you want to screen on this x, it's also possible, but but then I think ultimately it needs to relate it to this U somehow, right? Because if you want to screen on this x, probably you need to know the directional information, at least the directional. You need to know that if a higher x is better or a lower x is better, right? Something like that, right? So yeah, but yeah, that's a good question. I can think about it more. Okay, thanks.